So now we move on to the first iteration and we'll do the power update given those SIR values. So we can start at A, and we see that the A's receiver is going to feed back that value of 2.57, and A is going to look at it and it's going to adjust its transmit power of 2 milliwatts by looking at the current or the desired SIR, which is 1.8. So let's look at 2.57 versus 1.8. 2.57 is higher, which means right now the signal to interference ratio is too high. And we want to go down towards a lower SIR because we want to get everybody in the end to their desired SIRs so that nobody's asking for too much. So we can subtract 2.57 and 1.8 to get 0.77. And what that's saying is that right now the SIR is too high by 0.77. So in order to update the transmit power, DPC employs something that's very similar to that single-step TPC algorithm that we saw before, except that that ratio quantity that we said before is not defined in terms of power levels. It's defined in terms of signal to interference quantities. So if we look now intuitively here, we see that we're desiring a value of 1.8, and we have a value of 2.57. So it's too high, and we want the power level to go down. So best way to do that, the most reasonable way of doing that, is by saying, well, let's multiply the current transmit power by the ratio 1.8 divided by 2.57. So if we take 1.8 and divide that by 2.57, we're going to get a quantity that's less than 1. And it's that specific quantity which is telling us how much higher the current SIR is than the desired SIR. And then we multiply that by the current transmit power of 2 milliwatts. And so this quantity, the ratio here, comes out to be 0.7. And we multiply that then by 2 milliwatts, and we get 1.4 milliwatts as being the power level for the next iteration of A. Notice it is lower than what it was before because the SIR was measured to be higher. So we're trying to compensate for that. Now we'll move on to B. So B is going to feed back the SIR of 2.67 to the transmitter, and then it's going to look at its current transmit power of 2 milliwatts and its desired SIR of 2.0 and determine how it should update. And the update formula is going to be the same, but notice now that we have the same situation where this is too high. So the measured SIR is still too high right now. So you have 2.67 minus 2.0 gives us 0.67. It tells us how much higher it is than what it should be. And so we'll do the same thing again where we take this ratio 2.0, which is where we want to be, divided by 2.67, which is where we are right now, and multiply that by the current transmit power of 2. And we get that ratio quantity to be 0.75, which means that we need to lower it by 25% of what it is right now to get down to 2.0. And so 0.75 then times 2 is going to give us 1.50 milliwatts. Notice again that this is lower than this because this was higher than this. Now we'll move on to C, and C is going to feed back this 1.64 and look at it relative to the 2.2. So now we're in the exact opposite situation to what we were before. Now the SIR is too low, so the power level needs to go up. And it's too low by 2.2 minus 1.64, which is 0.56. And so we do the same equation again, where we take where we want to be divided by where we are right now, which is 2.2 divided by 1.64. But notice now that this quantity is greater than 1 rather than less than 1. And we multiply that by the current transmit power. So this transmit power is going to go up. And it's 1.34 times 2, which gives us 2.68 milliwatts. And notice now that this is higher than this because this was too low, so we're boosting that power level now. And so this is the equation, this is the actual DPC update equation right here. that the next power is equal to this thing called the ratio, which, as we said, is the desired SIR over the measured SIR, which is where we want to be over where we are right now, times the current power. And we do that at each iteration as we keep measuring the SIRs. So next question is, why do we have to do such an update? It seems pretty complicated, so why do we have to bother with it? Well, it turns out that this is looked at from a different standpoint. We're actually aligning each of the cell phones' incentives here. And basically what we mean by that is that we're forcing each of them to internalize the negative externality that they impose on the network by being there in the first place. And the negative externality here is in the form of interference. So the fact that A is in this network is going to cause interference for B and for C. So by making them follow this courtesy procedure, we make them say that if their SIR level is too high right now, that they will lower their transmit power and cut back in order to internalize the negative effect that they're imposing on everyone else in the network. Now, negative externality will be a recurring theme throughout this course, and we'll see it many times in many different contexts. It's one of the main themes of this course. And the way that that negative externality, as we said, is internalized is through a process called negative feedback, which we will take a brief detour to look at.